Hello, everybody, and welcome back to another session with the A4Q Testing Summit Edition 2025. I'm excited to be here with Elena Treshcheva, a passionate advocate for quality, innovation, and continuous learning in software testing. In this presentation, Elena will be discussing AI testing explainability, enhancing AI for testing with AI for mapping. Before I hand over to you, Elena, I just want to remind everybody that we will have a Q&A session at the end of this presentation. So pop your questions into the chat and then Elena can address them and discuss them in more detail. We also have our Best Presentation and Best Speaker Award. So go to the testingsummit.com website and submit your nominations for this presentation. Well, with that said, I'm not going to keep up everybody any longer. Elena, I would like to give over to you. We are very eager to hear what you have to say.
Yeah, hello. First of all, thank you so much for having me. Thank you for the introduction. My name is Elena Treshcheva, and I am a program manager at ExactPro. Indeed, let's see what I'm planning to share with you all today. So first of all, I'll make an introduction to the company I represent, as well as to the topic of our today's discussion. Then I will outline some of the AI testing aspects that are crucial for understanding the challenge of requirements traceability and test library explainability. And then I will share our vision on how the two are connected. And as a conclusion, I will try to frame it all as a set of takeaways. Okay, as I mentioned, I work at ExactPro. We are an independent provider of AI-driven software testing services for the financial industry sector. Our core service is using our model-based test automation framework to test complex financial technology platforms. And on top of that, we also provide our expertise in software testing to evaluate an enterprise test strategy and processes from AI testing perspective. What I am going to cover today is better to be started with the concept of software quality and how it is connected to the ever-pressing need for innovation. So with more available data and growing computational capabilities, we all see a rapid increase in the innovation pace across multiple sectors. So we work in financial technology sector, but it's not the only one, of course, but this one is not an exception, of course. So while we see the firms are enhancing their technology, and at the same time, they strive to preserve the value of their technology, of course. And by preserving value, I mean they want to avoid all the risks that is associated with the technology transformations. And the value delivered by the innovation can be viewed as measured across three dimensions: quality, cost, and speed. So, and of course, when we innovate, when we provide our software testing service, we need to take all of those three dimensions into account. Present-day systems that we are tackling are extremely complex, and this growing complexity is reflected in the structure and the way those systems operate. No matter whether those systems are AI or non-AI based, they are highly non-deterministic in their behavior due to combination of multiple conditions at play. Like, to name a few examples, you can see them on the slide. So it can be like some, almost infinite combinations, permutations of the data points, complex interaction between different systems like upstream, downstream systems. It also can be the multitude interoperability of multiple protocols, APIs, and all of that, of course, can be further exacerbated by environment conditions, as well as, of course, by human users' behavior. Here on this slide, for example, there's a high-level diagram of a financial technology platform. To be precise, it's a schema of a trading platform in a stock exchange. So usually mission-critical platforms are built in a way to avoid some like having a single point of failure. But even in the approaches, like with most thorough testing, right, there can be multiple minor flaws at every layer of the system defense, and like this. Sometimes those layers can be aligned in such a way so that there is a probability of a failure, and this can be illustrated by the Swiss cheese model that is referenced on the right side of this slide. So, speaking about the 3 dimensions of the value that can be delivered by the software, it is important to make sure that our enhanced software platforms continue to deliver value. And defects, software defects, is something that tends to decrease this value for the stakeholders, of course. So quality strategy should be built in such a way so that it targets the defects, the potential source, or decreasing the value from multiple standpoints. But how do we even tackle this level of complexity, right? So this is one side of the question. Another one is that we provide software testing service, and we also are in this race of innovation. And also we should ask ourselves, like from the perspective of our testing approach, like how do we perform it faster? How do we perform it cheaper and more efficient? And of course, one may say that the evident answer to that question would be through automation, of course. So software testing is a process of empirical technical exploration of the system under test with the intent of finding and describing defects. And defects, as I mentioned, is something that decreases the value of software system. The task of software testing consists of several steps. First of all, we have to select a subset of possible actions to perform against the system, right? Then we execute this set of the actions, and after that, we observe the outcome, we interpret the outcome, and if needed, we readjust and repeat the whole process. With modern approaches to CI/CD, for example, it is easy to minimize human involvement in some parts, namely in the part that is connected to test execution, and automating more higher level cognitive functions such as test idea generation or test result interpretation. It's of course something that we consider to be much less straightforward task. But of course, with the new technologies on the rise, we are trying to solve this challenge by adopting various model-based and data processing techniques on different steps of the software testing cycle. And when we do automate different software testing tasks, every step of the way, it's inevitable that the resulting approach should rival the system under test in its complexity. So that last sentence was said not to prepare you not to be scared by this slide. So again, this is a very high level overview of how we at ExacPro view a test approach that we consider suitable for testing sophisticated financial technology platforms. And the solution that I will be talking about today, it is something that we are trying to build on top of this approach, of this current approach that is depicted on this slide. So what is shown here is a model-based software testing framework that is centered around the test data. And it is something that uses a set of machine learning techniques on different stages of the software testing lifecycle. So to frame it into like a more structured view, here's a set of those steps. So you can see that we start our journey from test basis analysis, where we extract important conditions, important points. Then we prepare an input data set. We enhance this data set. We enrich this data set with the help of the model, which helps us iterate through multiple data permutations and target all the edge cases, all the difficult combinations that we cannot approach manually. So this is it. And then once we have everything, we run that through our tool, and we inject the resulting input data sets into the system under test. Then we deal with some outcomes. So then we deal with some test execution data, and we try to interpret it again with the help of our model, with the help of some additional scripts. Based on what we receive, based on what we see, we refine the model. And of course, the whole exercise is a continuous cycle targeted at test reinforcement, learning, fine-tuning, and like repeating the whole life cycle. So this is this circle diagram on the slide represents the continuous nature of this work, like the iterative nature of this work. So let's take a look at what is actually so special about this approach. So these steps, okay, this is quite a complex approach, as you can see. But here I wanted to outline 3 points that make this approach really effective, and what I consider like that it is the main thing that makes it really work as effectively as it does today. So a very important architectural decision of the approach is that we separate the 3 key elements of the test automation process. Of course, when we speak about test automation, it's inevitable, like nowadays, it's inevitable that we are speaking about using some test automation tooling. So one of the key constituents is the test automation framework that we use to interact with the system under test, as well as to manipulate with the test execution data. So the tool should be, of course, up to the task to work with concurrent data flows across multiple users and protocols. It also should handle massive arrays of data to support large-scale combinatorial checks, and also at the same time to be able to assess the system behavior, not only from the functional perspective, but also from the non-functional perspective as well. The second big element of the approach is the model, which we usually explain through the concept of a digital twin of the system under test. And what really stands behind this metaphor is a set of Python scripts that capture the behavior of the system under test. So one can say that it is actually the functional logic of the system flows, some rule-based scenarios, some rule-based logic, some other crucial things that we can observe in our system under test, right? But in the software testing cycle, this model has several main functionalities. So, as I said, the model represents, it captures the logic behind main functionalities like rules, conditions, state transitions. And on top of that, the model captures the protocol specifics of messaging, of the messaging that de facto reflects those rules, like on the API interaction level. So that's actually what is being sent from system to system, right? So this is how it is represented in real life. So, and the model is crucial at the stages of automated test generation, because the model iterates through all the through the multiple possible combinations of the data points. And also it is crucial at the stage when we can enrich our input data set with some expected outcomes, right? So when we are talking like thousands of scenarios, it's impossible like to describe each and every output manually. So we have the model do that instead of us. So this enrichment is really a crucial step of the overall process. And the third element, very important element, is the data. The main principle here is to store the data, the test execution data, separately from the message injection modules, as well as from the model itself. The simpler the format, the better. This is important for our data-driven approach, as we can access the original data, the original test execution data. And it is important that we are able to evaluate and re-evaluate what we see in the data again and again. So what kind of data can it be? So it can be literally everything, like anything that we can see during the testing process, like from test basis analysis to what's inside the test library to some maybe known facts about how the system really operates, like what are the known defects in it. The model-based approach means constant iterative improvement of our knowledge about the system under test. And the principle of the data being stored separately allows us to perform those checks when we update our model without the need to actually run the tests again and again against the actual system. So it is a very powerful approach, in a sense that we can fine-tune the model, but not without like the need to deal with heavy traffic of the data. So yeah, we can just use the same data, but evaluate it using fine-tuned set of rules and see the updated results. So as you can see, in our approach, we deal with a lot of data, which is something that really enhances the whole concept of test automation. And quite ironically, it is also a source of a challenge. So when the testing approach is built around the data, when it deals with thousands of test scenarios, massive arrays of test execution artifacts, it is extremely difficult like to report back to stakeholders as to what checks were really triggered by the framework, which requirements were covered, and what test execution results mean overall, right? And what does that mean in the context of software testing, as a service, right? And why this challenge is important. First of all, software testing is an information service, like in the first place. But what information should be provided, and what information has the most value? So that can be very different from the perspective of different stakeholders, or maybe rather different stakeholders may focus on slightly different aspects of what testing brings to the table, right? So here we have a powerful tool and a lot of task execution data on the one hand, right? And the data on uncovered defects. So that's one side. And another side of that would be how this measures against the agreed scope. Like how does that traced back to the requirements, right? So thus, if we like evaluate this from the point of view of the testing team, or test manager, we like to bring the most value for the software testing exercise, we need to deliver the value across both of these dimensions, like balancing out our main task, like the principal task of software testing, like of finding defects through massive automation. And yet, at the same time, we need to be able to quickly report on the coverage, and we should be able to quickly explain like what's inside a certain fragment of our test library. So remember, it was generated in an automated mode, right? So when we perform test management activities, right? So it is important to understand where we have everything, like every part of the puzzle. So this brings us to the concept of the requirements. Requirements can be human readable, they can be in the machine readable form. And of course, if we are here in the test automation mindset, we might think that the machine readable format is more natural for that, right? So it definitely seems like a better choice, but in reality, it's quite challenging. Like I'm not sure whether it's possible at all, like to find projects where the requirements would not be communicated in the human language form, right? So, and this is even without mentioning that some requirements may be unstated, like they can be implied, they can be derived from other requirements, like instead of being directly stated. So, given that, how do we map those onto our automated library that contains thousands and thousands of test scripts? So there is a very nice explainer, like a set of educational videos dedicated to machine learning. And the starting point for any machine learning related exercise is captured in full by the picture on this slide. So this is our first step. So label all the things. So what should we label exactly? So as I mentioned before, a key element of our test approach is the model. So we may want to find the data points for this model to label. Broadly speaking, when we look closer to the labeling problem, there are two types of information that we essentially need to identify within our test execution data, within our test approach, maybe. Something that is known to us as a set of facts, that would be one group, right? That can be some declarative information like lists, values, something like that. A type of the knowledge is how something is actually operating. What is the state transition sequence? What is the order of the events that are triggered by a particular set of values in the system? So it's more a dynamic nature, right? So maybe something that is more similar to events rather than declarative descriptions of what we have. So in existing approach, we already tackle some of this data, some of those types of information. To be more precise, when we use our model-based task generation, and also when we are at the stage when we add interpretations into our task execution results. So at all those steps, the model creates annotations. So the labels are created automatically, they are added to the data, and if we look at them, like try to classify them, to group them, we can see that uh, they're not the same. They are rather represent multi-layer information. So again, this is something that we do already, and we can see that this information can be of the first type, right? A more declarative type, like we can mention action parameters. We can label the area of the testing that is triggered by the test case. We can label the component of the system. Of course, a very important thing is to label the interface, because it is like the message structures vary from protocol to protocol. So the exact values, exact names of the fields will be different for different protocols. So this is also something that we need to label, right? On the other hand, there are some dynamic aspects of how the system under test operates, and what we were able to capture from this dynamic event, like as a sequence of events. So we also can label that. In this case, like on a deeper level, that would be the most more procedural part. So we can see that on the right side of the slide. So we can describe the state of the system before and after the test is actually run. If we continue with the examples that I provided earlier, the example around the trading platform, that would be, for example, the state of the order book in an exchange. So meaning that it is a state of the exchange before we sent an order and after we sent an order, for example. So the model also adds labels to mark some parts of its own code that were triggered by a particular test case. So this is also some way to add a dynamic aspect to that. And on top of that, you can see those parts in gray. So why they are in gray? So they are not directly represented in the approach as annotations. Yet those two parts, they are something that that is related to these two types of information, right? So first of all, we have it like ingrained in our testing tools, that we have tool codex, we have tool dictionaries, which basically is a machine readable specification that we have inside our tool. So some declarative information is already present in the tool. And at the same time, when the tool executes the tests and captures test execution data, it also stores the logs, the log files. So this is some dynamic data aspect that is recorded from the system under test. And also, there are some trace files that connect the observed information to the tests, to the actual test scripts that triggered these events that are captured in the logs. So again, this is an existing approach, and this is crucial for understanding of our next step. And what we have as a next step, it is a transition from what we have, and what we have is on the left side of the slide, to something else, right? So our further deeper step would be to create a solution that would build upon this labeling approach, to use annotations for mapping test artifacts to human readable requirements and human readable specification documents. So this is our vision. When we started to evaluate the task and select the approach for this next step, it was only natural for us to look at some established techniques in the natural language processing domain, and as many nowadays do, to evaluate the applicability of large language models to our case. Both have their upsides and downsides. So our current vision is to try and go with a hybrid approach and benefit from either of them. Why? Just because effectively we are dealing here with very different data. So some slides ago, I talked about the difference between human readable and machine readable specifications. And what we have in tool dictionaries and system annotations, this is structured data. This is very formalized data. Like if you look at it from the perspective of like what kind of data is contained in these annotations, one may consider that it is already a machine readable specification of the system under test. Like we can imagine a totally artificial situation when no one knows how exactly their own legacy system works, right? And they say want to obtain this knowledge like through operational cycle replay. So when we do that, like we obtain this data, and this data will be the only source of our requirements specifications that describe the system under test. So this is an artificial example, of course. So what I wanted to say that we have structured data, the data that have a very structured nature. And on the other hand, with the requirements, with the human readable requirements, we have the specifications, the description of of how the system operates, but in a human readable form, in the form of a natural language, right? So thus we need to use some approach. So most commonly it is considered to be effective to use large language models to transform human readable requirements into the data points. So, and we also see potential in using likelihood prompts to compare the vectorized representations with the underlying data. This vectorized representation comparison, this is something that is that comes from more established approaches of when established machine learning algorithms, like something that has been around for quite some time. So this is how we decided to combine the two and go with a hybrid approach. So, and in our case, it boils down to the labels and formal descriptions are, in their turn, are closer to the formalized descriptions. Yeah. So we, in our approach, we try to marry the two representations. Okay. while addressing the problem of mapping the requirements to the software testing artifacts, we've gone through the following reasoning steps. So first of all, we acknowledge the complexity of the present day software technology platforms. And we agreed that to tackle those platforms effectively, we need an equally sophisticated tool. Also, when we tackle testing on such a large scale, so most probably that would be model-based approach. Why? Because when we have thousands of test scenarios, it is pretty easy to generate lots of the data permutations, data points. But we also, in this case, we need to take care of all the outcomes, all the expected outputs that we expect to receive back from the system under test. So, and this is really hard to tackle without modeling approach. Next takeaway, next part of our train of thought would be that the test data is really crucial and it should be treated as a data set. And most preferably, this data set should be processed and it should exist in an isolated form. So it can be separated from the execution part, from the modeling part, and thus it can be captured independently so that the model can be evaluated without running the tests again and again. Next part of the discussion was about the traceability and explainability as two opposite sides of the same process of delivering the value of the informational service that we do during software testing. So, regarding traceability and explainability, it is something that we consider to be possible to achieve through extensive labeling, like our approach here, label all the things. And this labeling, like when we say label all the things, that means that all the things can be the types of information. It can be the factual data, it can be more dynamic data, and also it can be applied to different types of test artifacts. It can be applied to test cases, to data points in those test cases, and it can be applied to human readable documentation. So this is everything I have for you today. And I think I'm ready for your questions now. Thank you.
Perfect. Thank you, Elena, for this wonderful presentation. And we do have a couple of questions that our audience has sent through that they would like you to address. So let's have a look at them. What do you think is more important for a stakeholder of the system, to get an exclusive test execution information or see how it's mapped to the requirements?
Yeah, I was on mute, sorry. That's a very hard question because when we try to deliver value to our stakeholders, we have to see from their perspective, right? So the point about the traceability, about how what is the status like, or what is the progress status of how we cover the requirements, that may seem as more important exercise. But from what I've seen so far, the stakeholders are also interested in learning about the dynamic status of the system as well. So if we talk about a stable system, so that say we are past that stage when the regression exercise does not uncover too many of the defects. So it's always important to understand what's changing in this system. Like complex systems are also the ones that are that are most non-deterministic. So it's the dynamic aspect of the system state that is also important to fully understand the technology at hand. So when we have this traceability solution, this is of course important. But I'm like surprised to see that stakeholders also like take their time to ask like, okay, you have such a big library. What's actually changed during the execution? So
Thank you so much for answering that question. Our next question: have you already started to implement the vision you just shared? If so, can you speak of any challenges that you faced during the actual implementation?
um, yeah. So as I mentioned, we at Exactpro have been labeling the data since the inception of our current model-based approach, and now that we are starting to implement our next step of extending it towards the mapping to requirements, it becomes apparent that the task is quite challenging if we look at the system under test in the entire context of how it operates. So not only on as scenario level, like because like when you come up with a test scenario, like either you or the model, like whoever calculates the expected outcome for you. So it goes through a certain path, right? But something can take another course of action in the actual during the actual task execution, and what you planned to be targeting one line of the requirement, like one condition, one, let's say, decision branch, right? So something slightly changes, and instead of going according to this line, your actual test execution, the same input data triggers a slightly different atomic requirement. So this is something that is a real challenge, and that's why it is so difficult, like to come up with this approach, right? So it is not enough to add labels to test cases. It is really important to take into consideration like what we have after the test execution of this same test scenario. So,
Well, thank you, Elena. We have more. How do you tell your stakeholders that the depth of testing does not demand, example, 100 test cases?
not sure I do understand the questions. The question.
How do you tell your stakeholders that the depth of testing does not demand, example, 100 test cases? Does that make sense to you?
If we are talking here about the complexity of the information that we communicate to the stakeholder. This is, of course, this is difficult, like to provide a full interpretation of multi-thousand test library, right? So if you aim not to exceed like a certain amount of test cases, I think this is not feasible if we want to target each and every edge case and try to see to look at the system from multiple perspectives. So instead of like reporting like on the scenario per scenario basis, we should target the more high level chunks, like the areas, the certain functionality groups, something like that. So I would say that the labeling approach can help with that. So rather than identify the certain requirement coverage, we go and we report on a certain functionality area.
Perfect. Thank you. Well, we have reached the end of this session, and I want to thank you, Elena, for taking part in the A4Q Testing Summit, and everybody that's joined us this entire day. We still have a couple of streams coming your way. And just a quick reminder that we have our best speaker and best presentation award. So please visit the testingsummit.com website and submit your nominations for those awards. And then also all the presentations will be available to rewatch on the testingsummit.com website and our social media channels. So thank you very much again, Elena, and everybody. And I hope that you have a wonderful rest of your day and enjoy the rest of the streams that we have coming your way. Thank you so much.
Thanks for having me. Thank you.
Thank you.
Software testers. Move beyond theory and master testing with the AI-powered ISTQB add-on Practical Tester by A4Q program. The ISTQB add-on Practical Tester by A4Q equips you with the theoretical skills and practical competence to truly excel. Learn how to apply black box testing like a pro. Estimate accurately, write flawless defect reports, and catch issues early. The ISTQB add-on Practical Tester by A4Q complements your ISTQB certification by turning knowledge into powerful action. Visit our websites and find out more information.